You know, there is this old saying in security circles, security through obscurity. And usually when people say that, they're kind of rolling their eyes.
Oh, yeah.
It's meant to be a criticism. Like, just because you hid the key under the doormat doesn't mean you actually, lock the door.
Right. It's the idea that secrecy alone isn't security. I mean, if someone finds the mat, they find the key, and your security is just zero.
Exactly. But today we are looking at something that kind of challenges that whole notion. We're looking at a tool that says, okay, sure, lock the door, bolt it shut, but then let's build a fake wall in front of the door, paint a mural on the wall, and make sure the mural looks so boring that nobody ever stops to look at it.
That is a very, very vivid way to put it.
Yeah.
We are talking about digital spycraft today.
We are. And the weirdest part, we aren't looking at a tool made by, like, the CIA or the NSA. We are looking at a plugin for an AI art generator.
Specifically, we are doing a deep dive into the Orion4D SecretAgent suite.
SecretAgent, subtitle, Nodes for Covert Operations.
It sounds like a movie prop, doesn't it? But I mean, looking at the source code you sent over, the Python files, the documentation, this is surprisingly serious engineering.
So for the listeners who might not be deep into the generative AI scene, let's set the stage. This all runs inside something called Comfy UI.
Right. And Comfy UI is... It's the interface most power users run to generate AI images. It's node-based. So you connect these little boxes with virtual wires on a screen.
Yeah.
Box A loads a model. Box B, you type a prompt like cat in space. And box C generates the image. It's usually, a creative playground.
People use it to make anime, landscapes, architectural mock-ups. It's for making pretty pictures.
Usually.
But then you install this Orion4D SecretAgent pack, and suddenly, right next to your Generate Cute Cat node, you have nodes for AES GCM encryption, steganography, audio modulation, and spectrogram analysis.
It effectively transforms a graphics workstation into a signals intelligence station.
That's the hook for me. It's the James Bond factor. It feels like Q gave Bond a laptop, but instead of a gun hidden in a pen, it's a cryptography suite hidden in an art program.
And we really need to be clear here. This isn't just a toy. The underlying technology, which we will definitely unpack it, involves legitimate military-grade standards. We're seeing Reed-Solomon error correction. We're seeing Chatrwani encryption.
Yeah.
This isn't just writing LO in white text on a white background.
So here is our mission for this deep dive. We're going to take this suite apart, node by node. We're going to look at how it handles the sort of three big pillars of spycraft.
Okay.
First, steganography hiding the message. Second, storage turning images into hard drives. And third, transmission, how to move that data using everything from high-tech audio chirps to really low-tech Morse code.
And we should probably talk about why you'd want to do this. I mean, it's not just for spy.
Oh, absolutely. Privacy advocates, archivists, people making those alternate reality games, those ARGs. Or maybe just someone who wants to know if their private image is actually private.
It's going to be a technical ride, but I think the implications are they're fascinating.
Let's jump right into the first section then. The art of invisible ink. Steganography.
The word itself comes from Greek. Steganos, meaning covered or concealed, and graphene, writing. Covered writing.
So unlike encryption, where I send you a scrambled mess and you know I'm hiding something.
Right. With steganography, the goal is that no one even knows a message exists in the first place. You send a picture of your dog, a sensor looks at it, scans it, sees a dog, and lets it through. But mathematically, that dog is a container.
The Orion4D suite has a few ways to do this. The most basic one in the file, steganodes.py, uses something called LSB, least significant bit.
This is the bread and butter of digital hiding. To understand it, you have to think about how a computer sees an image. A pixel isn't just a color, it's three numbers: red, green, and blue.
RGB.
Right. And usually these are 8-bit numbers, which just means they go from 0 to 255. So imagine a single pixel. Red is 200. Green is 100, blue is 50.
Okay, I'm visualizing a specific muddy color.
Now, in binary code, the number 200 is written as a string of 8 ones and zeros. The most significant bit is the one on the left that carries the most value. If you flip that, the color changes drastically.
Oh,
It might turn from red to black.
So it's a visible change, not good for hiding.
Exactly. The least significant bit, the one on the far right, that holds a value of just 1. So if the red value is 200 and I flip that last bit, it becomes 201.
Can the human eye even see the difference between red 200 and red 201?
Absolutely not. It is physically impossible for our eyes to distinguish that tiny shift. But to a computer, 200 is distinct from 201.
So that tiny difference, that 1 or 0 at the very end, is an empty slot where we can put our data.
That's it. You take your secret message, say the text, "meet me at midnight." You convert that text into binary, and then you overwrite the last bit of every pixel in the image with your message bits, one by one.
So the image is the message. It just looks like a picture.
Correct. But, and this is a huge but, this method is incredibly fragile.
How so?
Well, think about what we just did. We manipulated the tiniest, most delicate part of the pixel data. If you take that image and open it in Photoshop and just save it as a JPEG,
No, JPEGs compress things, right?
JPEGs compress things, and the compression is lossy. It looks at a block of pixels and says, these are all basically reddish-brown. Let's just average them out to save file space.
And when it averages them,
It destroys your least significant bits. It effectively scrubs the secret message right off the canvas. So if you use this tool, and then you upload the image to Facebook or Instagram, which automatically convert things to JPEG,
a message is gone.
poof, vaporized. You have to use lossless formats like PNG. The source code in that Steganodes.p file is very, very strict about this.
Now, the basic hide text node is cool, but I was looking at superstegano.py. The Superstego vault. That sounds a little ominous.
It's definitely an upgrade. I mean, the basic node just hides a string of text. The Superstego vault is designed to be a file system.
A file system inside a picture.
Yes. The code shows that it can accept inputs for up to 10 distinct text blocks and 4 separate image files.
Wait, really?
Yeah. It takes all of those inputs, bundles them together into a serialized archive, and then stuffs that whole archive into the host image.
So I could take a picture of a sunset, and inside that sunset, hidden in the pixel noise, are 4 other pictures, maybe maps or blueprints, and 10 text documents.
Exactly. It's like a digital nesting doll. But the Superstego Vault does something else that's really critical.
Right.
It doesn't just hide the data. It encrypts it first.
I saw AES GCM in the imports. That's the real deal, isn't it?
It is the global standard. AES stands for Advanced Encryption Standard. It's what banks use. It's what the military uses.
And the GCM part, what's that?
Gallows counter mode. It's a specific way of running the encryption that provides 2 things. Confidentiality, obviously, and integrity.
Confidentiality means nobody can read it.
Right. Even if someone knows there's a message in the sunset and they manage to extract the bits, without the password, it just looks like random static. They can't break it.
Okay, so what about integrity?
This is the cool spy feature. Integrity means the system can detect if someone messed with the file. So if an interceptor thinks, I bet there's a message here, I'll just randomly change some pixels to corrupt it, the AES GCM check will fail.
Oh, wow.
When you try to decrypt it, the software will say, authentication failed, data tampered with.
So it's like tamper-evident seals on a bottle.
Exactly. It prevents you from receiving a message that has been subtly altered by the enemy to mislead you.
That is surprisingly robust for a Python script running in an art tool. But I have a logistical question. Images have a finite number of pixels, right? You can't fit a Library of Congress inside a thumbnail.
No, you cannot. And that's a classic mistake people make with steganography. They try to overstuff the suitcase.
So how does the user know when to stop?
The suite includes a node called the Superstego Estimator.
I love that name.
It's a calculator. It looks at your inputs, the 10 texts, the 4 images, measures their file size in bytes, and then looks at your cover image dimensions. It calculates the available capacity.
It does the math. You have 2 million pixels, you need 3 million bits. Error.
Precisely. It outputs a capacity mask or just a simple Boolean check. It tells you you're going to need a bigger boat, or in this case, a higher resolution image.
And speaking of the image, does the kind of image matter? Is a picture of a blue sky the same as a picture of a forest?
Tremendously. Imagine you have a picture of a plain white wall. Every single pixel is 255, 255, 255. If you start changing pixels to 254 to hide your data, you might actually create a faint, visible pattern.
Mm-hmm.
The noise of the data stands out against the silence of the white wall.
So you want a noisy image to begin with.
You want texture. A photo of a gravel road, a forest with millions of leaves, a cyberpunk street scene with rain and neon lights. Visual complexity hides digital complexity.
Noise hides noise. That's a good rule.
It is. But there's one more trap we need to talk about in this section. It's in a file called cleansaveanode.py.
The clean save. I thought this was just a utility.
It's an OPSCC necessity. Operational security. You see, Comfy UI by design is very helpful. When you generate an image, it embeds the entire workflow into the image metadata.
The metadata, that's the hidden text file attached to the image header, right?
Yes. And it usually contains the prompt you use, the seed number, the model name, and a list of every single node in your chain.
Oh, I see the problem.
Yeah. Imagine you use a Superstego vault to encrypt a file called secret-base-coordinates.txt. Yeah. You save the image. You send it. The interceptor opens the metadata and reads, node, Superstego vault, input, secret-base-coordinates.txt.
You literally handed them the receipt.
You handed them the confession. It completely defeats the entire purpose of the steganography. You aren't hiding anything if the metadata is shouting about it.
So cleanse save and node.py just, wipes that.
It scrubs it. It parses the image data right before writing it to the disk and deletes the pinginfo and exif tags. It ensures the file is dumb. It removes the fingerprints of the tool that made it.
That is a detail that most people would forget, but for a secret agent suite, it's mandatory.
Absolutely. It's the difference between playing spy and being secure.
Okay, so that covers section 1, hiding things inside pictures. But let's move to section 2. Because sometimes you don't want to hide the data inside a picture. You want the data to be the picture.
This is where we cross the line from steganography to what the suite calls pixel mass storage.
Pixel mass storage, it sounds industrial.
It functions industrially. We're looking at pixelmassstorage.py.
Yeah.
And the concept here is, why waste pixels on drawing a cat when I can use every single pixel to store raw data?
So if I use this node, what does the output look like? Is it a picture of anything?
No, it looks like static, colorful, random, high-density noise. It's not a picture of anything. It is a visual representation of a binary file.
Like a QR code, but dense.
Much, much denser than a QR code. A QR code has to be readable by a camera, so it has big blocks. This uses individual pixels, and it uses color.
Right, because a black and white pixel is just 1 bit, but a colored pixel.
So it's 24 bits, 8 for red, 8 for green, 8 for blue. So a single dot on your screen represents 3 bytes of 3 letters of text, effectively.
I mean, that up fast.
It does. And the code uses a specific header, what's called a magic number, to identify itself. BPMS2.
PMS2
It's
bit.
Pixel Mass Storage version 2. So when the decoder node loads an image, it checks the first few pixels. If it finds the color values that correspond to the letters PMS2, it knows, okay, this isn't random noise, this is an archive. Decode it.
I noticed a really creative node in this section called the Pixel Milfoo from pixelmilfoo.py.
Ah, yes. The pastry node.
A milfoo is that French dessert with the layers of puff pastry and cream. Why is the node named that? What are the layers?
Because it treats the image channels as separate layers. In a standard image, red, green, and blue all mix together to make a color. This node splits them. It allows you to pipe 4 different data streams into the 4 channels of a PNG. Red, green, blue, and alpha.
Alpha's transparency, right.
Correct. So theoretically, you could use the red channel to store a text file of a public domain book, something completely harmless, that's your cover. But in the alpha channel, the transparency values that control how see-through the pixels are, you store your encrypted payload.
So I look at the image, it looks like red static. I decode the red channel, and it's just Alice in Wonderland. I think, oh, boring, and I move on.
Exactly. But if you knew to check the alpha channel, you'd find the real secrets. It allows for plausible deniability. You can say, look, I gave you the key, it's just a book. Well, the real data sits right next to it, completely unseen.
That is devious. I love it. But again, we run into the storage limit. A single 4K image is big, but it's not that big. If I want to back up a database or a huge video file or my entire My Documents folder, a single PNG won't cut it.
And that is why the suite includes pixelvideonodes.py.
Video storage.
Think about it. Video is just a sequence of images, 24, 30, or 60 images per second. If one image can hold a megabyte of data.
Get a 60-second video at 60 frames per second. That's 3,600 megabytes. 3.6 gigabytes.
Exactly. The Orion Pixel Video Encoder allows you to take a massive input file gigabytes in size, and it chunks it up. It generates thousands of these static noise frames and then stitches them into a video file.
But wait, we just talked about JPEG being a trap because of compression. Video compression is even worse. I mean, YouTube, Netflix, TikTok, they compress video until it's barely holding together.
You are absolutely right. If you save this as a standard MP4 using, say, the H.264 codec, the compression would smear the pixels. The data would be corrupted instantly.
So how does Orion4D solve this?
By using a codec you might not have heard of, FFV1.
FFV1.
It stands for FFmpeg Video Codec 1. It is a specialized, open-source, lossless video codec. It's actually used by professional archivists to preserve old film reels digitally.
Lossless being the keyword there.
Yes. It acts like a ZIP file for video. It compresses the file size to be manageable, but it guarantees that when you play it back, every single pixel is mathematically identical to the source. No data is lost.
So you create an .av file using FFE1. To a normal user, it plays as a video of .glitch art. Just 10 minutes of seizure-inducing flashing colors.
But to the Orion software, that video file is a hard drive. It reads it frame by frame, extracting the data from the pixels and stitching it back into the original file.
It's the infinite suitcase. As long as you have hard drive space, you can just keep generating frames.
And it essentially creates a kind of air-gapped backup. You can store your files in a format that doesn't look like files. It's camouflage for your file system.
It really blurs the line between media and data. We usually think of them as totally different things.
To the computer, it's all just numbers. This tool just lets us see the numbers directly.
Okay, moving on to section 3, the sound of secrets. Because pixels are great, but sometimes you don't have a screen. Sometimes you have a radio, or a phone line, or a podcast.
Audio data transmission. This is an area where Spycraft goes way, way back.
I was looking at the audiocryptnodes.py file, and I saw a lot of warnings. Experimental. Very sensitive. What's going on there?
That node uses a technique called PCM mapping, pulse code modulation.
Write that down.
It takes your data byte, say the number 128, and maps it directly to the amplitude of the sound wave at that moment.
The amplitude, so the loudness, effectively.
The loudness, yeah. It's the most direct translation possible. But sound is physical. If I play that sound over a speaker and record it with a microphone.
The volume changes. There's echo, room noise.
Exactly. If the volume drops by just 1%, the value 128 becomes a 126. The byte is changed. The file is corrupted.
So AudioCrypt is basically only for saving to a file on a disk. You can't broadcast it.
Correct. It's extremely fragile. If you want to broadcast data, if you want to send a secret message over a radio frequency or hide it in the YouTube audio track, you need something robust. You need a modem.
And this brings us to the screechy noises, modemnodes.py.
The sound of the internet in 1995.
The code mentions AFSK turbo, audio frequency shift keying.
This is how old dial-up worked. It uses two tones, a high tone for a 1 and a low tone for a 0. Boop, beep, beep.
But the turbo part implies it's faster than my old 56K modem.
Well, actually slower than 56K, but faster than the old 300 baud teletypes. The turbo mode in Orion uses very high frequencies, 3000 Hz and 5000 Hz.
Those are high pitches, sharp.
Yes. Higher frequencies have shorter wavelengths, which means you can switch between them faster without the sound muddying up. It allows for up to 4800 baud, so 4800 bits per second.
That's pretty fast for audio.
It is. But if you want the real modern tech, you have to look at ufdmnodes.py.
OFDM, orthogonal frequency division multiplexing, that is a mouthful.
It is the technology that runs the modern world. Wi-Fi uses OFDM. 4G and 5G LTE use OFDM. Digital TV uses OFDM.
So how does it work in an audio file?
Instead of one beep toggling back and forth, imagine a choir. You have 32 different voices or frequencies, all singing at the same time. Each voice carries a different bit of data.
Ah, so it's parallel processing.
Exactly. And the orthogonal part is complex math that ensures the voices don't drown each other out. They are spaced perfectly so the computer can hear each one distinctly.
And this is more robust.
Much more. The node Orion OFDM modem final includes Reed-Solomon error correction.
I've heard of Reed-Solomon. That's used in CDs, right? To prevent scratches from ruining a song.
Yes. It's the exact same principle. The algorithm adds redundant data extra math that allows the player to reconstruct missing pieces.
So if my audio transmission gets a little static, or a pop, or a dropout.
The Reed-Solomon code looks at the remaining data, solves the equation, and just fills in the blank. The message survives.
The documentation says this was tested with MP3 compression at 128 kilobps.
That is a huge claim. MP3 compression usually destroys data signals because it throws away unheard frequencies. If this OFDM node actually survives MP3, it means you could hide data transmission inside a song, upload it to Spotify or SoundCloud, and someone listening could be coded.
That is wild. And there is a specific sound to listen for, right? A chirp.
Yes. Synchronization is the hardest part of this. The receiver needs to know exactly when the data starts. The node generates a chup, a sweeping tone, woo, right at the start.
Like a bird.
Or a sci-fi scanner. When the decoder detects that specific sweep, it aligns its internal clock. It says, okay, the data grid starts. NW.
So if I'm listening to a weird ambient track and I hear a distinct whoop followed by some complex static, I should probably run it through the Orion decoder.
You might find something interesting.
There is one more audio trick here that I really liked, spectrogramnodes.py, the spectral encode.
This is less about data storage and more about Ghosts.
Ghosts.
Visual ghosts. You
Yeah.
know what a spectrogram is, right? It's a visual graph of sound. Time is on the x-axis. Frequency or pitch is on the y-axis.
Right, you see the bass at the bottom and the treble at the top.
This node works backward. You feed it an image, say, a picture of a face. It calculates the sound waves necessary so that if you ran a spectrogram analysis on that audio, the face would appear in the graph.
So to my ear, what does it sound like?
Nightmares. It sounds like weird, washing, metallic alien noises. Swish, grr, screech.
But if I open that noise file in some audio software and switch to spectrogram view,
The face stares back at you from the graph.
that is the ultimate hidden in plain sight, or hidden in plain sound.
It's often used in capture the flag hacking competitions,
Right.
but it's a valid form of steganography. Unless you are specifically looking for it, you will never see it.
Okay, let's move to section 4. We've done high-tech images, high-tech audio. Now we're doing what you've called retro future tech. And this includes one of my favorite concepts, air gapping.
Ah, yes. The air gap, the gold standard of security.
For the listeners, an air-gapped computer is one that is physically disconnected from everything. No Wi-Fi, no Bluetooth, no Ethernet cable. It's an island.
It's the only way to be 100% sure hackers can't get in remotely, but it creates a problem. How do you get your data out?
You can't use a USB drive because someone might have literally glued the ports shut for security.
Exactly. Enter the QRvideo.py node.
We all know QR codes, those square barcodes, but this node makes a video of them.
Yes. If you have a long file way too big for one QR code, this node chops it into chunks. It generates a stream of QR codes, frame 1, frame 2, frame 3, and so on.
Like a strobe light of barcodes.
Exactly. And you play this video on the screen of your secure air-gapped computer. Then you take your smartphone or another computer with a webcam and you point it at the screen.
You're filming the screen.
Optical data transmission. No wires, no radio waves, just light. The camera captures the QR codes, the software reassembles the chunks, and the file is transferred across the air gap.
That is spy movie stuff 101.
It is. And the code implements a little protocol to make it work. It embeds a header, O4D index total data.
Explain the protocol.
Well, imagine you're filming the screen but your hand shakes, or the camera loses focus for a second. You miss frame 50.
The file is broken.
Not if you have the header. The header tells the receiver, I am jump 50 of 100. So if the receiver misses it, it knows, I have a hole at position 50. It can tell you, hey, rewind and play that part again.
It makes the transmission state aware.
Precisely. And for the design lovers, there's also curative.py.
I saw options for squircles.
Yes, a squircle, a squared circle, very trendy in UI design. This node lets you make aesthetic QR codes. But the cool technical part is the masking.
Masking.
The node lets you put a logo in the middle of the QR code. Now, usually, covering up a QR code breaks it, but this node calculates a forbidden zone around the logo.
A no-fly zone for data.
Right. It forces the data bits to wrap around the logo. It ensures that the logo doesn't obscure any actual information. It maximizes scan reliability while still looking cool.
Now, from the high-tech visual to the low-tech audio, Morse code.py. Why in 2026 are we messing with dots and dashes?
Because the apocalypse might happen. No, seriously, Morse code is the cockroach of communication protocols. It survives everything.
It's robust.
Incredibly. A digital signal needs bandwidth. It needs clean frequencies. Morse code is just on and off. You can send it over a static-filled radio line. You can flash it with a flashlight. You can tap it on a pipe.
And the suite includes a full encoder-decoder.
It does. It can convert text to Morse audio, or even modulate an image's brightness to flash Morse code. And interestingly, it pairs with militarynodes.py.
The phonetic alphabet.
Alpha, Bravo,
Really
Charlie,
the French version. Anatole, Berthe, Celestine.
which I didn't even know existed until I read this code.
So why is this here?
Clarity. If you are using Comfy UI's text-to-speech features to read out a generated password or code, B sounds like D, P sounds like T, over a bad connection.
Ambiguity is the enemy.
Exactly. But Bravo, Delta, Papa, Tango are unmistakable. If you were generating number station, a synthesized voice broadcast, reading secret codes, you use the phonetic alphabet to ensure 100% accuracy.
And speaking of number stations, let's talk about the encryption itself. The simple cipher.py.
This is a nod to those creepy shortwave radio stations that just read numbers for hours.
12, 45, 88.
Right. This node takes your text, encrypts it with SHA-220 Poly 1305, our high-security friend, but then it outputs the result as a string of decimal numbers.
So instead of garbled text symbols like #@Ray, which might get blocked by a spam filter,
You get 12, 85, 99, 43. It looks innocuous. It looks like inventory data or coordinates or lottery numbers.
But it's actually the blueprints for the Death Star.
If you have the key, yes.
And to get the key, you need a password. And for that, there's generate passphrase v2.py.
This node teaches you about entropy.
Entropy is just randomness, right?
And predictability. The node uses the diceware method. It has a list of thousands of words. It rolls virtual dice to pick them. You get horse battery staple correct.
That famous XKCD comic method.
Yes.
Yes.
It's easier for a human to remember than X7J9 tag F.
Right.
But mathematically, it has very high entropy. The node actually calculates the entropy bits and tells you how strong the password is.
It's educational spycraft. I like that.
It forces you to use good security practices.
So we have generated the intel. We've hidden it in a picture or a video or a screeching audio file. We've encrypted it. Now we need to file the report. Section 5, the mission report.
Because even spies have paperwork.
pdfnodes.py. This felt oddly corporate to me.
It does, but it's powerful automation. This node uses the FPDF2 library to generate PDFs programmatically.
It creates a specific layout, right?
Like the code comments call it Steel, Sober, et Professional. Sober and professional. It censors images, it bolds the headers, it creates margins.
So imagine the workflow. You have an AI agent analyzing satellite photos. It detects a change. It crops the photo. It writes a summary.
And then instead of you dragging those files into Microsoft Word, the PDF report node automatically grabs them, formats them, and spits out a missionbriefing.pdf at the end of the chain.
It automates the bureaucracy.
Which is valuable time saved.
And if you were on the receiving end, there's acrotylitynodes.py.
OCR, optical character recognition.
This reads text from images.
Yes, it uses the Tesseract engine. This closes the loop. If you send data via the video QR method, you are receiving images. You need OCR, or the specific QR decoder, to tune those images back into text.
I really liked the Orion text comparator node, the diff check.
This is crucial for verification. It compares two blocks of text and highlights the differences.
Why is that in a spy suite?
Well, imagine you have a digital order and a photo of a physical order. You run OCR on the photo, then compare it to the digital original. The comparator will instantly flag if a single number has been changed.
It's digital forensics. It detects forgery.
Or corruption. It ensures that the message you received is exactly the message that was sent. In high-stakes environments, close enough isn't good enough.
So looking at this whole package, Orion4D Secret Agent, it really is a Swiss Army knife.
It is. It's a complete ecosystem. You have input via OCR or generation, processing via encryption, storage via pixel mass, transmission via OFDM or QR video, and then output via PDF.
And all of it running on the GPU that you bought to make pictures of waifus.
That is the irony. We bought these powerful graphics cards for art, but SecretAgent repurposes that computational power for heavy-duty cryptography and signal processing.
It's hiding the spy station inside the art studio.
And really, that is the best camouflage. Who suspects the artist?
So, who is this actually for? I mean, we joke about spies, but is it really for them?
I think it's dual-use technology.
Right.
Sure, an intelligence operative could use this. It's robust enough. But think about a dissident in a restrictive regime. The internet is monitored. Emails are scanned.
But pictures of cats are allowed.
Exactly. This allows that person to smuggle a banned book or a news report out of the country inside a harmless-looking video or image.
Or a whistleblower inside a corporation.
Or an archivist. I genuinely think the pixel mass storage using FFV1 video is a brilliant way to store long-term data backups on video hosting platforms. It's data preservation via visual media.
It blurs the lines. It makes us look at our files differently.
It does. It raises a question for everyone listening. We consume gigabytes of media every single day. We scroll past thousands of images on Instagram. We watch hours of video on TikTok.
How much of that content is just content?
And how much of it is a carrier? How much of it contains a payload that we just don't have the key to see?
In an age of total digital surveillance, maybe the safest place to hide a secret is right in the middle of a piece of AI-generated art, staring everyone right in the face.
Hiding in plain sight. Or plain pixels.
Check your checksums, everyone. And maybe run that weird-sounding song through a spectrogram.
You never know what ghosts you might find.
Thanks for taking this deep dive with us. It's been a mind-bender.
Always a pleasure.
We'll see you on the next one. Stay secure.